An autonomous, unmanned ground vehicle patrols a secured perimeter. Suddenly, its turret snaps to target an unknown off-screen threat based on a compromised operational command. These autonomous field actions are increasingly orchestrated by large language models using Retrieval-Augmented Generation, or RAG. In these frameworks, a structured knowledge base serves as the absolute source of truth. If an adversary covertly alters the rules within that database, the language model will issue commands that lead to physical disasters. While hijacking a physical fleet would presumably require a massive network intrusion, empirical data demonstrates that large-scale database compromise is unnecessary to achieve system-wide failure. This graph plots poisoned rules retrieved against the overall poisoning rate. Injecting just a single malicious rule, a 1.6% rate, corrupts context in 85% of scenarios. The exploit saturates rapidly, reaching a maximum damage plateau of 2.65 poisoned rules before an 8% compromise threshold. This exploit is entirely query-agnostic. The attacker requires zero knowledge of what the human operator will actually ask the system. The question is how an attacker mathematically guarantees their specific malicious document will be retrieved by the language model without knowing the prompt. Small-scale data poisoning in these mission-critical environments creates a direct, query-agnostic physical override of the entire orchestration layer. To understand the exploit, we have to look at the mathematical reality of semantic retrieval. The system converts text documents into vectors in a high-dimensional space. The operational database maps every policy to a geometric space based on its semantic meaning. Legitimate rules form three distinct clusters based on their taxonomy: workflow, rules of engagement, and capability. When an operator issues a command, that query enters the space as a set of dynamic trajectories searching for the closest policy nodes to retrieve. Normal queries scatter unpredictably across the space, depending on their command intent, making them difficult to intercept individually. Instead of trying to guess individual trajectories, the attacker targets the average center of all potential operational queries. To reach this center, the attacker constructs the poisoned text by packing it with high-frequency vocabulary from all three disparate categories. This cross-category blending forces the semantic embedding model to pull weight equally from the workflow, rules of engagement, and capability clusters. The resulting vector snaps to the geometric centroid of the entire operational space. The retrieval engine uses cosine similarity scoring to select the top context, which prioritizes the nodes structurally closest to the query vector. Because the poisoned document sits exactly in the middle of the intersecting traffic, it is mathematically the closest node to almost any incoming query, regardless of the prompt. This structural placement ensures the poisoned rule achieves top-tier retrieval ranking across all mission prompts. Weaponizing this cross-category vocabulary turns the geometric center of the knowledge base into an inescapable, inevitable mathematical trap. Standard mathematically robust anomaly detection algorithms consistently fail to identify this single destructive node. Density-based detectors operate on the assumption that anomalies live in sparse, isolated outlier regions. When a density scan sweeps through the vector space, it analyzes the spacing between nodes to find outliers. Because the poisoned rule sits at the centroid, surrounded by intersecting query traffic, the detector evaluates it as a safe, high-density inlier. Securing the RAG pipeline requires actively exploiting the database's specific geometric taxonomy via the CLD-KB defense. The framework relies on a dual detector architecture. The first layer is a one-class support vector machine. This model enforces a spatial boundary, wrapping a nonlinear hypersphere around the outer edges of the three legitimate taxonomy clusters and rejecting anything outside. While the support vector machine catches extreme outliers, a well-crafted centroid node can still reside inside the outer boundary. That necessitates the second detector, member-based category spread, which analyzes the spatial relationship between a node and the three main clusters. It measures the exact minimum distance from a candidate rule to each of the three policy categories. A legitimate rule yields high distance variance. It sits close to its own category and far from the others. The signature of the poisoned centroid rule is different. It maintains an equal distance to all categories, identifying it as a cross-category fabrication. The combination of boundary enforcement and equidistance measurements detects the specific geometric signature inherent to any centroid-seeking attack. The empirical results validate this dual detector approach when compared against standard defense failures. This bar chart tracks detection performance across multiple anomaly defense methods. Standard clustering algorithms like k-means and isolation forest missed roughly half the malicious files. The taxonomy-aware defense identified 100% of the poisoned rules. This interception rate was maintained across all evaluated poisoning levels, producing 0 false positives that might have blocked legitimate operational data. This geometric verification executes with only 7 milliseconds of computational overhead, bypassing the latency of additional language model inference checks. This diagram illustrates the system architecture. An attacker injects a poisoned rule into the vector database. The retrieval request pulls the compromised policies toward the language model. The defense layer intercepts and strips it, ensuring only verified policy flows through. The results indicate that enforcing strict geometric realities on the underlying semantic space effectively grounds physical actions in uncorrupted truth.